M.E.A.D.O.W is a sci-fi farming game that runs almost exclusively through shaders. Project M.E.A.D.O.W, standing for Mega Expansion Agricultural Decahedra Off-World, is an initiative established and funded by the GFGC, the Goldfish Galactic Corporation, to propagate the expansion of human and goldfish kind beyond Earth's limitations. The GFGC has recently finished construction of the 10th M.E.A.D.O.W, a cluster of terahedral megastructures in orbit around the 2.5 iteration of Earth. M.E.A.D.O.W 10 celebrates the 1,000-year anniversary of the truce between goldfish and humankind. The game, however, takes place in the 5th cluster, M.E.A.D.O.W 5. At the start of the game, the player obtains a force field protected plot of land on the 5th level of the game's primary terahedron, Epsilon. The plot of land starts small, but expansions can be purchased from the GFGC using the proceeds earned from the sale of crops and animal products. Tool upgrades and industrial equipment are also purchasable to increase the ease and effectiveness of farming. At maximum size, a tool can cover the span of the entire farm. While researchers have effectively removed limitations on tool size within a terahedron, water is still a scarce resource. In M.E.A.D.O.W 5, water is obtainable from infrequent GFGC-sponsored rain events, water reclamation equipment, and off-terahedron ice extraction. Each of these methods has a cost, especially in time, associated with it. So the player must find a balance between the farm's needs and their ability to source water. Water collection from rain events is outside of player control, while the other two methods are within player control. Water reclamation equipment is slow but consistent. Ice extraction is a manual player activity that requires a trip to a nearby terahedron and a ship with limited capacity. The farm's daily water requirements set the pace for production and will grow with the size of the farm. With further development, I would like to include a research and discovery-driven building and crafting system, where the player can construct helpful machines, additional storage, and animal housing structures. These will help expand the farm's capabilities. Crafting materials that are unavailable on the player's farm can be obtained from neighboring terahedra, similar to ice extraction. In order to explore the next essential systems in the game, it is necessary to examine a brief history of the world through the nearly 1,000 years between the year 2025 and present-day Earth 2.5. In the year 2025, it was a commonly held belief that the mind of a goldfish was quite limited. This, however, was and is a terrible misconception. In reality, the mind of a goldfish reaches backward and forward through the space-time continuum, only pausing on the present day for a few seconds at a time, usually as a last-ditch effort to remain alive by consuming sustenance. The discovery of this extraordinary ability to see through time led to the rapid disintegration of relations across the globe and the eventual outbreak of World Wars IV, V, and VIII. Further details of this history can be found in Human Relations, the third volume of the GFGC's Accurate and Complete Information Compendium, the most complete and unbiased source of all historic information in the known universe. As the GFGC constructed their meadows, a galactic fish market, or GFM, similar to the archaic stock markets 1,000 years ago, naturally developed. The GFM utilizes a goldfish-based trading model to predict futures. When setting up their farm, a player can choose to buy into the GFM and trade their goods on a fluctuating market, or they can sign a fixed-rate contract with the GFGC to sell their products for a standard rate that is consistent over time. While the GFM is a broadly accepted institution within the galaxy, it is not without fault. If the player is skilled enough to infiltrate the GFM headquarters and befriend the execufish, they will have the ability to influence the direction the GFM shifts for particular goods. This manipulation is particularly effective if they can discover the predictor fish's favorite food. A good enough meal will temporarily pull the predictor fish back to the present day long enough to move to the side of the tank with their unexpected but not unwelcome snack. Hello, I'm Zerico. I'm a full-time software engineer dabbling with indie game development as a hobby. I love breaking down complex systems through code and sharing what I've learned. I've been learning glsl and developing an interactive shader system over the last 3 months. The development of M.E.A.D.W began as a means to increase the functionality of my shader system within the Godot game engine. What I've covered so far in this video shows the core functionality of the game and some of its lore, but I do have plans to expand the scope of the game to include NPC interactions and a player-driven story. My other game projects include a little Metroidvania called SlimeRGB, a case study on Hollow Knight's design and a way for me to learn the Godot game engine for the first time, and a puzzle platformer called Kindled, where I built a procedurally generated pixel flame system that physically reacts to terrain. While working on Kindled, I realized I kept focusing on the systems behind the platformer and ignoring the actual level design of the game, which is a necessary component for any platformer. Despite trying to focus on that level design, I just couldn't stop turning to the systems of the game. This ultimately led me to move away from those projects and enter a more systems-driven genre, coalescing in me pursuing a procedurally generated survival crafter inspired by Valheim, a game idea entirely built on the groundwork of systems. Due to the nature of survival crafters being on a significantly larger scale than I'm used to, I decided to extract a single core system of the genre to build a smaller game around. M.E.A.D.W was born from this decision, letting me develop the survival crafter's planned farming system in isolation. When I finish M.E.A.D.W, I'll have a fully functional and robust farming system to integrate back into my larger game. This also gives me an opportunity to expand the functionality of my core shader system, and simultaneously gives me the experience of finishing and releasing a game. Level design is an essential skill that I'll eventually try to learn, just not right now. So, while SlimeRGB and Kindled are projects I want to finish in the future, my sights are set on system-driven games first. M.E.A.D.W doesn't use tilemap layer nodes or manage tile data on the CPU. My goal with the game is to avoid most forms of serialized processing, so I'm leveraging the GPU and its parallel processing capabilities. Godot builds a lot of functionality and data handling into their tilemap layer system, and even auto tiles for you, though all that extra power makes auto tiling expensive at runtime. Because M.E.A.D.W just requires rudimentary tile management and tile rendering, I'm very incentivized to come up with my own solution catered to my specific needs. Additionally, one of the intended ways to play M.E.A.D.W involves the player being able to see and manipulate every interactable tile on their map at once. After some experimentation, I wrote an early procedurally generated auto-tiled prototype that supported player manipulation on a virtually infinite viewport size. I later updated this prototype to integrate multiple layers of tile sets at once. Due to the shaders being fairly basic in function and the virtual memory used being fairly low, the entire system at large is extremely lightweight and performant. I want to share my game development progress on this channel, but I'm also excited to talk about how these shaders work. This shader system will be a free resource for anyone who wants to play with it, and that starts with me talking about the concepts and techniques it uses. I've always appreciated the free resources I've stumbled across during my own game development journey, so this is my small way of pitching in. As of right now, my shaders aren't in a user-friendly state. I refine the shader code fairly frequently, and a lot of my Godot manager scripts are pretty tightly coupled to it. I also want to integrate the system with Godot's tilemap layer nodes, to take advantage of Godot's powerful tile management. Once I stop making changes and decouple what I can, I'll build a GitLab repository with an example project that includes the shader system and how to use it. Until then, I'll be sharing updates on M.E.A.D.W and releasing standalone videos to explore technical concepts on a lower level. To help demystify what my shaders do, here's the high level for how the shader system operates. I currently use 4 shaders, 1 compute shader, 3 fragment shaders. Compute shaders excel at performing the same mathematical operation across a wide array of data simultaneously, while fragment shaders excel at controlling how pixels get drawn to the screen. You can consider the compute shader I use as the brain that informs the fragment shaders how to render the game. When the game starts, I generate a 256 by 256 pixel image. Each pixel represents one 16 by 16 tile. I call this the pixel map, because it's the pixel representation of the game map. Each pixel naturally comes with 4 color channels: red, green, blue, and alpha. These channels let me establish a line of communication between the shaders and the CPU, and is where I pack my tile data. I use the standard 32-bit color format with 8 allocated bits. Each channel can store a value in the range of 0 to 255. Godot's color nodes and shader language interpret these channels as floats, so they range from 0 to 1. It's easier to design custom behavior into these channels if we can come up with a way to convert these float values back into integer representation. I do this through color steps, which I define as the fraction 1 over 255. As long as I maintain the idea of moving through these channels in color steps, you can always multiply the float representation of a color channel by 255 to move back into integer territory. This lets me assign an enumerated type to a color value or use the value as an array index to reference helpful data. For example, I can define that a value of 255 in the red channel means a grass tile. The compute shader is responsible for managing these color channels and only gets called when the map requires a change to its tile data. As for the drawing of the map, I separated rendering into 3 fragment shaders: tiles, crops, and seeds. This helps with organization, but it also lets me isolate which sprites will render to the screen with a custom transformation, like rotating seed sprites or flipping crop sprites. An example of all this working together looks a little like this. The game's time has advanced by 1 time cycle and needs to advance the growth stage of watered crops. The CPU will send a grow command to the compute shader. The GPU, interpreting the command, will run through each pixel on the pixel map into these steps. It first checks for a wet soil tile, which is a red channel value of 253. Then it checks to see if a crop is growing on it, which is a green channel value greater than 0. Finally, it checks to see if the crop has reached its maximum growth stage, which is a blue channel value less than or equal to a constant value stored in an array, which is indexed by the crop ID value stored in the green channel. If all these checks pass, the compute shader will increment the blue channel by 1 color step. This change gets reflected by the fragment shaders because they use the blue channel as an index into a tile atlas to locate the correct crop sprite at the appropriate growth stage. Instead of iterating over tiles on the CPU, a system like this lets the player harvest, grow, or terraform their entire map at once without reducing performance. If you're interested in more detailed and technical explanations, keep an eye out for my standalone videos, the first of which will be auto-tiling on a dual-grid system. Regarding the future of M.E.A.D.W, I don't have a release date in mind yet for either the game or the shaders. I also don't have a Steam page right now, but I can make one if there's interest. If you have any ideas you'd like to see come to life in M.E.A.D.W that make use of its shader system, feel free to throw them at me. By design, M.E.A.D.W runs on systems that are fast to iterate on, which lets me playtest the game and make rapid and dramatic changes to see what sticks. I'd also love to hear about what kinds of games that you think this shader system would work well for. If anything I've talked about so far interests you, feel free to subscribe, but you can always just check back in every once in a while to see what's new. Until next time, stay curious, and try not to drop your sheep into the void.